So here's another problem. A bicycle accelerates from rest to 8 meters per second in 20 seconds. It stays at 8 meters per second for 20 seconds. And then it comes to a stop in 10 seconds. Let's graph this motion. And so I'm going to graph velocity versus time, right? Here's my velocity, and we'll put that in meters per second. And here's my time, and we'll put that in seconds. And I guess I'll have maybe something every 10 seconds, 10, 20, 30, 40, 50. So 10, 20, 30, 40, 50, and then 2, 4, 6, 8, 2, 4, 6, 8 meters per second. Let me try that one more time. 8 meters per second. And so it starts here. It starts at rest at the initial time. 20 seconds later, it's going at 8 meters per second. So I would do that. Right? And now I want to say it stays at 8 meters per second for 20 seconds. So I'm going to, this goes up to there. Say, this goes up to there. And so it does this. Right? And then it comes to a stop here in 10 seconds. Something like that. I could probably do that line just a little better, maybe. Like that. That's its motion. And so, you know, we could ask all kinds of questions. We could say, what's its acceleration in this range, right? It's 8 meters per second. So I can call this, you know, acceleration 1. A1 is the change in velocity over the change in time. That's equal to 8 meters per second minus 0 meters per second over 20 seconds. And that's 8 over 20, which is 0.4 meters per second squared. Right? A2 is just 0. Ask yourself how I know that. Right? The slope of a horizontal line is 0, and since the acceleration is the slope, right? And then I can calculate A3. A3 is same change in velocity over change in time, and so it's the final, which is 0 meters per second, minus 8 meters per second over 20 seconds, over 10 seconds. Minus 0.8, sorry, 0.8 meters over second squared. So that would be the acceleration here. And you can see this is a steeper slope, so it's got a larger acceleration, but it's negative. This is 0.4, this one's 0.8. This one's upward, but it's not as steep as this one is downward. And so I have different accelerations in different regions. I could, okay. So we can start talking about velocity and acceleration as ways to solve kinematics problems, and we've done some examples. Once again, we said the velocity is the change in position over the change in time, and the acceleration is the change in velocity over the change in time. We can do a little notational work here, and we can say, look, delta x is equal to x final minus x initial. Often we write that as just x minus x naught. We use this for x final. It's just whatever our position is we're interested in, really. And x naught represents x initial. Similarly, we say delta v is equal to v final minus v initial, and that's often written this way. Again, this is really the average velocity we're talking about when we talk about the change in position over the change in time. And so if we're being careful, we would say it that way. And so, so these are the two changes in velocity. So we could write this as v average is equal to x minus x naught over delta t. But we're going to let delta t which is t final minus t initial, is just, we're just going to call that t minus 0, or just t. We're going to say, look, our stock clock is always going to start at t equals 0, or almost always. And so this becomes v average is equal to x minus x naught over t, and similarly the acceleration is v minus v naught over t. Now we can rearrange these, and this one becomes x minus x naught is equal to v average times time, if I multiply both sides by time, or I can say x is equal to x naught plus v average times time. Similarly, I had a little spot of water there. Similarly, I can do the same rearrangement here, and I can say v is equal to v naught plus the acceleration times the time. These two equations carry the same information that these two equations do. They've just been rearranged. And so when we write these equations down, we'll usually be talking about them this way, but they're just an algebraic rearrangement of this way. So we can use those equations to solve a problem like this one. The car accelerates from 20 meters per second to 40 meters per second in 10 seconds. How far does it travel in this time? Right, well, they're asking how far, and so what we're looking for is, x minus x naught, right? That's what how far means, right? It's the final position minus the initial position, right? And they've given us v naught, right, and v, which is our final, and then t. And so we have these two equations, basically. We have x equals x naught plus v average times time, right? And this is the one that's going to solve this for us. This is really just delta x, right? How far does it travel? And so I can say x minus x naught is equal to v average times time, right? And so I have to figure out what the average velocity is, right? And so the average velocity, we haven't thought about this before. If it starts at 20 and ends at 40, it's the initial velocity plus the final velocity divided by 2. It's 20 meters per second plus 40 meters per second divided by 2, which is 30 meters per second. Hopefully you can see that if I know the initial and final velocity, that if I want the average of those two, I just add them and divide by 2. Same way if you had a 20 on a quiz and a 40 on a quiz, the average score you had would be 30, right? The key here is this assumes constant acceleration, which we'll be doing most of the time in this course. There are a few times when we start later in the semester where we'll allow the acceleration to not be constant, but this is a really good approximation for most things like cars and bicycles and things that are falling and that sort of thing. So, and so now we can solve this problem. We can say, look, x equals, I wanted to use this equation, right? X minus x naught is equal to v average times time, and so that's 30 meters per second times 10 seconds, which is 300 meters per second times seconds. The seconds cancel, which is 300 meters. And so that's how far it traveled. And we got sort of an additional equation we hadn't really talked about before, which defines the average velocity as not just the change in position over the change in time, but also the initial plus the final velocity is divided by 2 as long as the acceleration is constant. A car traveling at 10 meters per second accelerates at 2 meters per second squared for 15 seconds. What's its final velocity, right? And so what we're looking for here is v, right? And what we have is, since it's initially traveling at 10 meters per second, that's v naught. This is the acceleration, and this is the time, right? And so we can say, look, from our formula from earlier, v equals v naught plus the acceleration times the time. That's 10 meters per second plus 2 meters per second squared times 15 seconds, which is 10 plus 30 is 40 meters per second. So that's my final velocity, is 40 meters per second. Then I can ask, what is its average velocity, right? And so we can use that formula that we came up with on the last slide, which says the average velocity is the initial velocity plus the final velocity divided by 2, which is 10 meters per second, plus 40 meters per second divided by 2, which is 25 meters per second. That's its average velocity, right? And I can say c how far does it travel in this time? Well, x equals x naught plus v average times time. We can just assume our x naught is 0. I know in the previous problems I was subtracting it over the other side because delta x is x minus x naught. But we'll just pick x naught equal to 0. Since the problem hasn't told us, we can just choose that. And so we can say this is equal to 25 meters per second times 15 seconds, which is 375 meters. Suppose I had asked you from the beginning, instead of my first question being what's its final velocity, suppose I said how far does it travel in this time? So I just say a car traveling at 10 meters per second accelerates at 2 meters per second squared for 15 seconds. Right? Imagine that I had said this. Right? The only formula we have for how far it's traveled is this one. And so we would still have to go through all the previous steps of first calculating what the final velocity is, then calculating the average, and then plugging into this. And so in the next slide, I'm going to do a little algebra with the equations we have already and come up with a few more equations that will help us solve a problem like this, for example, in one problem with one equation.